Part 4, Controlling Access to a REST API. Now we'll look at the mechanisms that API Gateway supports to control and manage access to your API. With API Gateway, you can optionally set your API methods to require authorization. When setting up a method to require authorization, you can use AWS Signature version 4 or Lambda authorizers to support your own bearer token auth strategy. You have a few options for authorizers in API Gateway. The first is not to use one, and instead leaving your access open. The second is IAM. The third is based on JSON Web Tokens. You could also use Lambda. Setting your API to authorize by using IAM means your client application is using IAM credentials. Usually, these credentials are temporary ones with the use of the client-side SDKs. All requests that are not signed requests from the SDK return a permissions error to your SDK. JSON Web Tokens, also called JWTs, are used in the background when using OpenID Connect, known as OIDC or OAuth 2.0 to authenticate. REST APIs can use Amazon Cognito as their JWT authorizer, and HTTP APIs can use third-party providers. When a request includes a JWT, API Gateway evaluates the request. It determines the request's scope of use and ultimately validates whether this user can access the resource they're requesting. This can also validate against users in an Amazon Cognito user pool. You can configure distinct authorizers for each route of an API, or use the same authorizer for multiple routes. To create a JWT authorized API, you must have an identity provider to use. Amazon Cognito is a simple identity provider you could use. Lambda authorizers are Lambda functions. With custom request authorizers, you can authorize access to APIs using a bearer token auth strategy such as OAuth. When an API is called, API Gateway checks if a Lambda authorizer is configured. API Gateway then calls the Lambda function with the incoming authorization token. You can use Lambda to implement various authorization strategies, for example, JWT verification, OAuth provider callout that return IAM policies to authorize the request. If the policy returned by the authorizer is valid, API Gateway will cache the policy associated with the incoming token for up to 1 hour. You can use AWS credentials to sign requests to your service and authorize access like other AWS services. The custom API Gateway SDK generated for your service manages signing an API Gateway request. You can use Amazon Cognito to retrieve temporary credentials associated with a role in your AWS account. Enable authenticating a user by validating their tokens through checking the issuer, client ID, timestamp, signature, and authorization scopes when specified. This authorizer provides seamless validation of Amazon Cognito user pools tokens, or any standards-compliant OIDC and OAuth 2.0 tokens without the need to write custom code. This option can be set up quickly and supports basic user validation. JWT and Amazon Cognito user pool authorizers do not require any custom code. You would first create the authorizer and then update the API route to use it. The code snippets on this slide illustrate how you would use the AWS CLI to make this update. As mentioned, a Lambda authorizer is a Lambda function that API Gateway calls for an authorization check when a client makes a request to an HTTP API route. You can use Lambda authorizers to implement custom authorization schemes to comply with your security requirements. With a Lambda authorizer, you first send the request to a Lambda authorizer function. The purpose is to validate that the request meets your custom criteria. The result is passed to the end target, often another Lambda function. If you choose the new 2.0 format version when configuring the authorizer, you can return either a Boolean value or an IAM policy. The Boolean value enables simple responses from the authorizer without having to construct an IAM policy, as illustrated in the example on the slide. As a result, the code in your end target function can more gracefully handle a rejection, it is preferable to returning an abrupt 400 error from an API gateway to the client. Here are the key takeaways for this section of the module. API Gateway supports the following protections from unwanted traffic: resource policies, client certificates, AWS WAF, CORS, and throttling. API Gateway supports the following options for authorizing access to resources: IAM, JWT-based authorizers, and Lambda authorizers. Thanks for watching. We'll see you in the next video. Monitoring a REST API. API Gateway integrates with Amazon CloudWatch by sending log messages and detailed metrics to it. You can enable logging for each stage in your API or for each method. You can set the verbosity of the logging and whether full request and response data should be logged. API Gateway can send detailed metrics to CloudWatch, such as the number of API calls, latency, integration latency, and HTTP 400 and 500 errors. CloudWatch Logs provides optional logging of errors and access information for REST APIs that you configure by stage. You can also enable access logging to log who has accessed your API and how it was accessed. An access log is a single log line that is written out for each request that hits your API Gateway instance. They serve as a general summary of the request: what time the request occurred, the HTTP method and path that was requested, and the response latency. API Gateway creates the log groups and log streams for error logs. To use access logging, create the log group and then point a stage to that log group when you enable access logging on the stage. You can choose from common formats, for example, common log format or CLF, and JSON. Before we finish this section, we'll look at some other monitoring tools, beginning with AWS X-Ray. With AWS X-Ray, you can identify performance bottlenecks and errors and pinpoint issues to specific services in your application. X-Ray helps you answer questions such as, what is the breakdown of this individual transaction as it passed through my application? And where are problems occurring across my distributed application? With X-Ray, you can configure services to capture trace data about the requests. For some services, including API Gateway, you can directly enable X-Ray. X-Ray combines the trace data from each service involved in serving a request into a unit called a trace. For developers, it provides visual detection of latency distribution, provides quick isolation of outliers and trends, and makes it easier to debug application code. You can also filter and group requests by error type. With AWS Config, you can discover existing AWS resources and export a complete inventory of your EC2 related resources, such as instances, VPCs, and elastic IP addresses, with all the configuration details. You can also determine how a resource was configured at any point in time. These capabilities enable compliance auditing, security analysis, resource change tracking, and troubleshooting. AWS Config helps you answer two questions. The first is, does this modification comply with our rules? And the second is, how do these resources relate to other resources? AWS Config provides a normalized snapshot of how your resources are configured and lets you create rules that enforce the compliant state of those resources. An AWS config rule represents the desired configuration settings for specific AWS resources or for an entire AWS account. If resources violate a rule, AWS config flags this as non-compliant and notifies you through an Amazon Simple Notification Service or Amazon SNS. The AWS CloudTrail service helps you log the API calls made in your AWS account across regions. Because everything in AWS is an API call, activity to your AWS resources, such as starting and stopping instances, creating or modifying databases, or uploading a file to Amazon S3, are logged, regardless of whether that action was performed through the AWS CLI, an SDK, the console, or an API directly. This is a crucial tool to help simplify your governance, compliance, and risk auditing. CloudTrail helps you answer 3 questions: which resources were modified, who modified the resources, and when were they modified. CloudTrail is enabled when you create an account. When activity occurs in your AWS account, that activity is recorded in a CloudTrail event, and you can see recent events in the event history. The CloudTrail event history provides a viewable, searchable, and downloadable record of recent CloudTrail events. Details of API actions include the identity of the requester, time of the API call, request parameters, and response elements returned by the service. Thanks for watching. We'll see you in the next video. Optimizing API Gateway. One way to optimize API Gateway is by enabling API cache. With response caching, you can reduce the number of calls made to your API endpoint and also improve the latency of requests to your API. When you enable caching for an API stage, the API Gateway service caches responses from your endpoint for a specified TTL in seconds. API Gateway responds to the request by looking up the endpoint response from the cache instead of making a new request to your API endpoint. This means the API request is served quickly. Note that caching is priced hourly, whether the cache is used or not. API Gateway provides a couple default metrics to help you understand how the cache is being used. First is the cache hit count, the number of requests that were served from the API cache in a given period. Second is the cache miss count, the number of requests that were served from the backend in a given period when caching is enabled. Another way to optimize API Gateway is through payload compression. Compression reduces the amount of data that is sent from API Gateway to clients, which can reduce costs and improve the performance of your APIs. API Gateway allows your client to call your API with compressed payloads by using one of the supported content codings. By default, API Gateway supports decompression of the method request payload. However, you must configure your API to enable compression of the method response payload. You can also send compressed requests from the client. Compressing data of a small size might actually increase the final data size. Compression in API Gateway and decompression in the client might increase overall latency and require more computing time. Run test cases against your API to determine an optimal value. You can enable compression for an API using the API Gateway console, the AWS CLI, or an AWS SDK. This slide shows an example of what the uncompressed and compressed payloads look like. Thanks for watching. We'll see you in the next video. Let's review the module and wrap up with a practice certification exam question. In this module, you learned how to recognize APIs, describe API Gateway, indicate the steps for developing REST APIs with API Gateway, and how to use API Gateway to create, publish, maintain, monitor, and secure APIs. It's now time to complete the knowledge check for this module. Now, let's take a look at a sample exam question. A developer is building a web application that uses API Gateway. The developer wants to maintain different environments for development and production, dev and prod workloads. The API will be backed by a Lambda function with 2 aliases, one for dev and one for prod. How can the developer achieve this result with the least amount of configuration? A, create a REST API for each environment and integrate the APIs with the corresponding dev and prod aliases of the Lambda function. Then deploy the 2 APIs to their respective stages and access them by using the stage URLs. B, create one REST API and integrate it with the Lambda function by using a stage variable in place of an alias. Then deploy the API to 2 different stages, dev and prod, and create a stage variable in each stage with different aliases as the values. Access the API by using the different stage URLs. C, create one REST API, integrate it with the dev alias of the Lambda function, and deploy it to a dev environment. Configure a canary release deployment for prod where the canary will integrate with the Lambda prod alias. And D, create one REST API, integrate it with the prod alias of the Lambda function, and deploy it to a prod environment. Configure a canary release deployment for dev where the canary will integrate with the Lambda dev alias. Consider the answer choices and rule them out based on these key requirements. Let's pause a few seconds before discussing the correct answer. If you need more time to consider the answer choices, pause the video. The correct answer is B. With deployment stages in API Gateway, users can manage multiple release stages for each API, such as alpha, beta, and production. Using stage variables that can be configured, an API deployment stage can interact with different backend endpoints. Users can use API Gateway stage variables to reference a single Lambda function with multiple versions and aliases. Thank you for completing Module 6, Developing REST APIs. Thanks for watching. We'll see you in the next video.
Hello, and welcome to Module 7, Developing Event-Driven Serverless Solutions. Welcome to Section 1, Introduction. At the end of this module, you should be able to explain serverless computing, describe how Lambda works, recognize Lambda invocation models, and identify how to use AWS Identity and Access Management, or IAM, to grant Lambda permissions. You should also be able to indicate the steps to author and configure a Lambda function, explain how to deploy Lambda functions, identify why AWS X-Ray is a critical developer tool, and create Lambda functions. This module includes sections introducing serverless computing and Lambda, invoking Lambda functions, setting permissions for Lambda, authoring and configuring Lambda functions, deploying Lambda functions, and monitoring and debugging tools for application developers. Sophia finished using the mock endpoints to test the API, and now she wants to launch the dynamic version of the Cafe website. She needs to update the API integration to connect to the backend database. Sophia will replace the mock endpoints with functional endpoints and use a Lambda function to bridge the connection between the APIs and the data stored in Amazon DynamoDB. This diagram gives an overview of the application you will build through the labs in this course. The highlighted portions are relevant to this module. As highlighted in the diagram, you will configure Lambda functions to be invoked by the Cafe website calls to the REST API endpoints configured in API Gateway. One of the Lambda functions will query and return data from DynamoDB. Thanks for watching. We'll see you in the next video. This video covers Section 2, Introducing Serverless Computing. One benefit of cloud computing is you can abstract the infrastructure layer to alleviate many operational tasks. You can focus more on the business logic for your applications instead of managing instances, operating systems, or servers. Everything that's required to run and scale your application with high availability is handled for you. Serverless computing eliminates infrastructure management tasks such as server or cluster provisioning. The reduced overhead also means you can experiment and innovate faster. You don't pay for any infrastructure when the code's not running, and it runs only when needed. With servers, you must think about configuring instances, updating your OS, installing the application platform, configuring automatic scaling and load balancing, building and developing applications, continuously patching, securing and monitoring servers, and monitoring and maintaining applications. With serverless, you can focus on building and deploying applications and monitoring and maintaining applications. From a builder's perspective, abstracting infrastructure into the cloud from virtual servers to containers and now to serverless has changed application development. It coincides with a move away from monolithic applications and towards service-oriented architectures and microservices. The ideas of distributed applications and microservices aren't new, but the evolution of cloud services makes it easier to build applications that follow a few principles. First, use small, loosely joined pieces and purpose-built data stores. This strategy provides flexibility to make changes without affecting other parts of the system. This flexibility also helps you to scale and deploy pieces independently and to incorporate reversible decisions. Next, use specialized integration services to increase the speed of delivery and decrease the effort of integrations between services. Finally, write infrastructure as code to automate as much of the deployment process as you can. This approach makes it simpler to replicate environments and deploy more frequently with minimal overhead and greater confidence. Serverless is an efficient approach to modern applications. First, with serverless compute, you can focus on writing business logic, while someone else handles scaling and high availability. Second, with purpose-built serverless databases, you can choose the features and capacity that suit the type and volume of data that each service needs. Next, managed services provide API proxy, messaging, and orchestration, and have pre-built integrations with some AWS services. With this process, you can connect services using asynchronous event-driven patterns to achieve decoupling and flexibility. This also reduces the undifferentiated lifting of building integrations to connect your components. Finally, serverless deployment frameworks makes it easy to use infrastructure as code for deployments and automate the deployment pipeline. With monolithic application, things start out easier. It's simpler to build and test, and you only have one artifact to deploy. For some less complex applications, a monolithic approach might be the best option for a long time. For complex applications that grow over time, the interdependencies among components and the coordination among teams become more difficult. These concerns can decrease developer productivity. First, you have one technology stack to develop in. You must hire and train developers in that technology. Any change to the technology stack becomes a major project. Then you have a single database. The most demanding use case drives your cost and capacity. Operations that aren't suited to the database or data structures will continually be tuned to strive for better performance. However, they'll reach a limit where it's impossible to improve without a redesign. From an operational standpoint, many developers are pushing changes through a shared release pipeline. This causes friction at many points of the lifecycle. For example, to add a new feature to a shared library, you must convince everyone to upgrade at the same time. To quickly push an important fix, you still must merge it with everyone's in-process changes. This leads to merge Fridays, or worse yet, merge weeks, when all developers compile changes and resolve conflicts for the next release. After development, you face overhead when pushing changes through the delivery pipeline. You must rebuild the entire application, run all the test suites to check for regression issues, and redeploy the entire application. Every new feature adds to the complexity of the coordination, deployment, and ongoing operations effort. Technical debt stacks up, and it becomes nearly impossible to untangle code. With a modern serverless application, the effort to get started is higher. Moving to microservice-based development requires a significant surge in effort, as everyone learns and makes mistakes. Often everyone is new to the required approaches. Moving from experiments and utilities into full-scale production applications requires a surge of effort that includes both technology and organizational changes. The energy it takes to get past that initial stage can hold organizations back. After the initial learning curve, the agility of this approach starts to accelerate the release of new features. It also reduces the effort to keep them running. What benefits do microservices provide? You can scale individual services independently. You can choose the best technology stack and data store for each service. You can deploy changes independently as often as desired. And you can focus on a specific service and innovate within that service. Thanks for watching. We'll see you in the next video. Introducing AWS Lambda. Lambda is a serverless compute service that you can use to run code without provisioning or managing servers. What are some of the benefits of Lambda? Lambda invokes your code in response to events that you configure, scales automatically based on demand, and incorporates built-in monitoring and logging with Amazon CloudWatch. Functions and event sources are the core components of Lambda. An event source is the entity that publishes events to Lambda. A Lambda function is the custom code that you provide, which processes the events. Lambda runs your function on your behalf. To use Lambda, start by uploading existing code or writing code in the Lambda editor. Then set up your functions to run when events occur in other AWS services. Functions can also respond to incoming HTTP requests, consume events from a queue or stream, or run on a schedule. Lambda runs your code only when activated and uses only the necessary compute resources. You pay only for the compute time that you use. Lambda provides many features. First, it offers the ability to bring your own code. You don't need to learn a new code language. In addition, development in Lambda is not tightly coupled to AWS, so you can easily port code in and out of AWS. Second, Lambda integrates with and extends other AWS services. From within your function, you can do anything that traditional applications can do. For example, calling an AWS SDK or invoking a third-party API. Next, it offers flexible resource and concurrency models. Lambda scales in response to events. You configure memory settings, and AWS handles the details, such as CPU, network, and I/O throughput. Lambda also offers a flexible permissions model. Lambda uses IAM to securely grant access to your resources and give you fine-grained control for invoking your functions. Lambda provides built-in availability and fault tolerance. It's a fully managed service, so high availability and fault tolerance are integrated into the service without any additional configuration on your part. And finally, Lambda reduces the need to pay for idle resources. Functions run only when invoked, so you don't pay for idle capacity. You can use Lambda in various ways. Web applications and real-time stream processing are two common use cases. Other use cases include the following: backends, data processing, chatbots, Amazon Alexa, and IT automation. Anything you want to do with servers, you can probably do with Lambda. Use Lambda and serverless to reimagine your approach to new or updated applications. As a developer, you create functions that the Lambda service manages. When you create a function, you define the permissions for the function and specify which events will invoke it. You choose a runtime and create a deployment package that includes your application code and any dependencies and libraries necessary to run your code. And finally, you configure parameters such as memory, timeout, and concurrency. When your function is invoked, Lambda provides a runtime environment based on the runtime and configuration options that you selected. Lambda initializes concurrent environments to maintain the pace of invocation requests up to certain quotas. Lambda supports multiple languages through the use of runtimes, including Node.js, Python, Ruby, Java, Go, and .NET. You can also implement a custom runtime if you want to use another language in Lambda. Each invocation of a Lambda function runs in an ephemeral environment, one that is initialized on demand, lasts a brief time, and then is removed. Lambda manages creating and tearing down these environments. You don't have direct control over these environments. Concurrency is the number of Lambda function invocations that are running at one time. Lambda provides the environments on demand as it receives requests, which is how Lambda quickly scales horizontally. Several factors can influence concurrency. First, reserved concurrency on a function is an optional value per function that reserves a subset of the regional quota for the function. This value also establishes the maximum concurrent instances that are permitted for the function. Second, the regional quota is the total number of invocations that can run concurrently across all Lambda functions within an account by region. AWS sets this number as a soft quota on the account. Next, the burst quota prevents concurrency from increasing too quickly if a large spike of requests occurs in a short time. You cannot modify this limit, and each region has one. Request rate and function duration is the rate at which new invocation requests for the function arrive, in conjunction with how long Lambda takes to run the function. Finally, the event source is where Lambda manages concurrency of requests in different ways, based on the type of event that invokes it. Here are the key takeaways from this section of the module. Lambda is a serverless compute service that integrates with other AWS services. You can use Lambda for many use cases, including web applications, backends, and data processing. Lambda functions run in on-demand temporary environments. Thanks for watching. We'll see you in the next video.